Imagine a spinning object so powerful that it literally drags space and time around with it. This mind-bending phenomenon, predicted by Einstein's general theory of relativity, is known as frame dragging. While this effect's almost impossible to notice in our daily lives, the universe gives us natural laboratories to observe it on a much larger scale. Einstein's theory tells us that any spinning body, no matter how big or small, warps the fabric of space-time around it. For example, the Earth's spin causes a tiny frame dragging effect, so small that detecting it requires incredibly precise instruments, like the Gravity Probe B satellite. This satellite, which cost $750 million, detected frame dragging by measuring minuscule changes in gyroscopes, changes so tiny that they amount to just 1 degree every 100,000 years. Fortunately, the universe contains many natural gravitational laboratories where physicists can observe these phenomena. In a recent study published in Science, researchers revealed evidence of frame dragging on a much more noticeable scale, using a radio telescope and a unique pair of compact stars orbiting each other at dizzying speeds. This cosmic dance involves a white dwarf and a pulsar. A white dwarf is a remnant of a star that has exhausted its hydrogen fuel. It's similar in size to Earth, but hundreds of thousands of times more massive. These stars can spin incredibly fast, rotating every minute or two. Now, imagine the frame dragging caused by such a rapidly spinning white dwarf. It's about 100 million times stronger than the Earth's. But how do we observe something so far away? Enter the pulsar, a dense, rapidly spinning neutron star. Discovered 20 years ago by CSIRO's Parkes radio telescope, this pulsar orbits the white dwarf in just under 5 hours. Every minute, the pulsar spins 150 times, sending out a lighthouse beam of radio waves that we can detect from Earth. By timing the arrival of these radio pulses, scientists can map the path of the pulsar as it orbits the white dwarf. The data reveals that the orbit of this stellar pair, officially called PSR J1141-6545, is slowly tumbling in space, a clear sign of the white dwarf's frame dragging effect. But how did this unique system come to be? When pairs of stars are born, the more massive one dies first, often leaving behind a white dwarf. Before the second star dies, it transfers matter to the white dwarf, causing it to spin faster and faster. Eventually, the second star explodes in a supernova, creating a pulsar. The white dwarf's intense spin drags space-time along with it, tilting the pulsar's orbital plane, a phenomenon we've observed through years of patient research. Einstein once believed that many of his predictions about space and time would never be observable. Yet, we've seen a revolution in extreme astrophysics in recent years, with groundbreaking discoveries like gravitational waves and the first image of a black hole. And now, thanks to 50-year-old radio telescopes and the dedication of scientists, we're able to explore general relativity in ways even Einstein never imagined. If you enjoyed this deep dive into the mysteries of the universe, don't forget to like, subscribe, and hit the bell icon for more incredible science stories. Thanks for watching.